Hey, Dr. Lane, welcome to S9. I'm doing problem 28. We got a disc, a string wrapped around it being pulled at 9 newtons by a hand. So imagine a hand here and a hand here. And we got the measurement of the change in the distance of masses and the measurement of the change in the hand here, because the hand was here. And A asks us, at this instant, what is the speed of the center of mass of the disc? So for this one, we got to look at the point particle system. And we know that the change in energy in the point particle system is equal to work, which is force times distance of the center masses. And we can rewrite this as a change in kinetic transitional energy is equal to work. And we can further rewrite this as 1/2 mv squared equals force times distance of the center masses. And then we just solve for V. And now we have it in a nice little formula that has all our knowns here. So 2, force, 9 newtons, change in center masses is 0.11 meters. Over 2.1 kilograms, it's equal to 0.971 meters per second. And B asks us, at this instant, how much rotational kinetic energy does the disk have relative to its center of mass? So for this one, we got to look at the extended system, because we're looking at, now we got the hand included. We're not just looking at just this piece here. We know the change in energy of the extended system is also equal to work, but this time it's of the hand pulling, not of the distance of the particles. And we can rewrite that as the change in kinetic transitional energy plus the change in kinetic rotational energy is equal to work of the hand. And we know from the point particle system that the change in kinetic transitional energy is equal to force times distance of the center mass here. Then we rewrite that, solve for just the change in kinetic rotational energy, and just do some algebra, plug in our knowns, and we get 1.53 joules. And C asks us, at this instant, the angular speed of the disk is 7.5 radians per second. What is the moment of inertia of the disk? So for this one, we got to use the kinetic rotational energy formula, which is kinetic rotational energy is equal to 1/2 moment of inertia, angular speed squared. And then you just solve to get the inertia on its own. That's what all this algebra is doing here, which you really just switch and flip, which I should have just did that. But yeah, so that's what that's doing. And then you get inertia is equal to 2 kinetic rotational energy over angular speed squared. And then we just solved for the kinetic rotational energy, which was 1.53 joules. That gave us the angular speed. And then we end up with 0.0544 kilogram meters squared. And yeah, that's it for today.